All right, so I did get one question this morning, and it was about doing the discussion boards, and this is for organic. So what y'all are stepping into right now is alkanes. So alkanes are the first functional class we're looking at. These are CH3, CH2, CH, no double bonds, no triple bonds, just straight carbon-hydrogen bonds. And the challenge with these is the naming. So naming is the first thing we're going to start with every functional group beyond here. So when we go to alcohols, alkyl halides, alkenes, alkynes, ethers, we're always going to start with naming, but alkane naming tends to kind of be the foundation off of which all these things are built. So if you can name an alkane, you can easily name an alcohol or an alkyl halide or something like that. So when it comes to alkanes, the real struggle with these is that because everything is carbon-hydrogen bonds, there's really nothing particularly unique about this molecule. We're going to struggle to do two things. One is find the longest chain, and two, figure out who the number one carbon is. So I was asked specifically number 1 and number 5 on the board. So we'll do number 1 and number 5. And 5, 2, 4, 6, 8, 10. Yep, no me. So to understand the naming of alkanes, I think it's good to understand the history that this is a very German science. And Germans are very utilitarian in their approach to pretty much everything, especially when the era and decades that this was coming out. So we're talking like 1900s-ish. So the goal here is to keep it simple. We're going to talk about an ambiguity that comes up with the rules, but generally speaking, there are no ambiguities with the rules, and it's very, very utilitarian in how you approach it. So all organic compounds are named right to left. Your instinct is look left, right, because that's how you read. But really, we're going to start with the right side of the name, and we're going to work our way to the left. So the first thing you have to do is identify the longest chain, and this is the challenge with 2 and 4, is determining what would be the longest chain. So in this case, I've got this bit here is the longest chain. It has 1, 2, 3, 4, 5, 6, 7, 8. So this is octane. So the oct here is for 8, and the ANE means an alkane. So our longest chain here is an alkane, and it has 8 carbons in it. Now we need to figure out how many other branches are in it. So what I'm going to do is I'm going to start counting them up. I have 1, 2, 3, 4, 5, 6 methyl groups. So this is a hexamethyl. Octane. So the hexa here is to indicate 6. The meth means that they have 1 carbon, and the YL means branch. So, not branch. So when we say that this is hexamethyl, there are 6 methyl branches coming off of it. Now we need to number them. And this is where an ambiguity actually kind of exists. It says in all textbooks we name to minimize the number of the first group. But it's not clear, are we referring to the group as they appear on the drawing, or do we refer to the group as they appear in the molecule? Now, for 90% of the molecules you come across, this is not going to make a difference. But definitely if you start getting like really complicated molecules, you'll actually see even books disagreeing with each other on how to name it. The joy of the IUPAC naming is that even if you name it entirely wrong, you can still redraw it. So kind of the nice fail-safe built into the system is that even if you name it wrong, you probably can still draw it from the name, even if the name is wrong. Now, for me, the way I was taught, the way I think the spirit of the rule works, is that you're going off this group. You're going off the name. So if we had a methyl, we had an ethyl, we had a butyl, we'd actually memorize the number relative to those. But in this case, we've got nothing but we've got nothing but methyl groups. And so we want to minimize the number. We want to start with the number of carbon being the one closest to the first methyl group. So if we start from here, it's 1, 2, 3, 4, versus if we start here, it's 1, 2. So we're going to start numbering right to left. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 methyl groups here. So 2, 2, 4, 4, 5, 5, hexamethyl octane. The 2's 2, 4, 4, 5, 5. We have to designate the position of every single methyl group because there's ambiguity. If you say, well, why can't I just put 2, 4, 5? well, what's to stop there from being like a group on like the first carbon or the sixth carbon or the seventh? And if you said, well, you know, we've only got 2, 4, 5 listed, that should be really obvious. They're on 2, 4, 5. Let's say I only have 5 methyl groups. There's one methyl group missing. There's one carbon that doesn't have 2 methyl groups on it. You haven't specified where they are. So if we had just 2, 4, 4, 5, 5 pentamethyl, okay, which one of those doesn't have the 2 methyl groups on it? That's why you have to specify the position of each. But the number here needs to match this prefix. So since I have a hexa, I need to have 6 numbers in front of it. So 224455 hexamethyl octane. Now, with this one on the right, if we have a ring, what we need to do is we need to specify the long. Okay, so if we have a ring, we have to figure out if the ring is longer than the alkyl chain or if it's shorter. So in this case, this is a 5-member ring. It's shorter than our 8 or 10 here. So 2, 4, 6, 8, 10. So our longest chain here is the decane. But if this chain were shorter than the ring, we would name it, and that's what some of the other problems are. One of the other problems is if the ring is bigger than the alkane chain, it becomes an alkyl branch on the ring. If the ring is smaller than the alkane chain, it becomes an alkyl branch on the ring. So this is cyclopentane. Since it's a branch, we need to name it cyclopentyl. So the cyclopentyl here tells us that it is a ring and it is an alkyl branch. Now we also have a methyl. So how do I know the methyl goes before the cyclopentyl? Well, it is based on the alphabetical order. So M comes before P, but you say, well, cyclo starts with a C. The cyclo here is a prefix. So prefixes get more ignored. If I had 2 methyl groups and I ended up getting a dimethyl, we would ignore the di and just purely go off the methyl. So the cyclo here is a prefix. A di here would be a prefix. We ignore those. The groups are always listed in alphabetical order, ignoring their prefixes. So now if we go off this system, we need to minimize the number of the first group. In this case, if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it would be 2 methyl, 7 cyclopentyl decane. Now, joy of the IUPAC system with this is going the reverse is really, really easy. So if I had a 224455 hexamethyl octane, well, I know the parent chain is octane, so I do 1, 2, 3, 4, 5, 6, 7, 8. And I know I have 6 methyl groups. I can put this as the first one. So 1, 2, 2, 4, 4, 5, 5. These two are the same molecule. I've just flipped it 180 degrees. I've just rotated it just to kind of give you a little bit of challenge. Same thing's true here. Cyclopentyl decane. I start from the right. I have decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 methyl. 3, 4, 5, 6, 7. Cyclopentyl has 5. So that's how we do the naming. Again, we're going to start on the right side, find the longest chain, name it, and name the branches before it. They're all going to end in YL because they are branches. That's what the YL designates as a branch. They're going to have prefixes, either to designate them as a cyclo group or designate the number of those particular groups. We're going to ignore the prefixes. They're going to be listed in algebraic order. And then the way I was taught, the way I teach it, we're going to minimize the numbering in the name. But you'll definitely find some textbooks that argue you're supposed to minimize it based on how it's drawn. Again, I don't see why you would do this. This is really not in the spirit of IUPAC because it makes it complicated. Now you have to look at the figure. This takes all the guesswork out. Whatever group comes first, that's closest to the first carbon. So that's it for questions I had asked this morning. I'm not seeing anyone in the chat room. So if you've got a question, please feel free to ask it. I got the chat open. I'm going to get some work done. Again, these are lessons. These are live streams. They are not lessons. They are not lectures. So unless you have a question, there's really nothing for me to talk about today. So you got a question about the pre-lab. Pre-lab consists of 5 things. You're going to find these in the syllabus: the title, the purpose, the summary of the hazards, summary procedures, and let's see here, title, oh, and the date. So mostly it's just you summarizing what the procedures are, so that if I took your lab notebook away, took away your lab manual, you could actually do the lab, so right down in that level of detail. And as far as the purpose, it needs to be a summary of the purpose. So again, this is all in the lab syllabus. It documents what's required for the pre-lab and what needs to be included. Also, if you download the lab syllabus or the lab notebook rubric, this is on the course website. Under the writing tutorial, there's also a rubric, and it discusses in the rubric, like by each lab, the summary of what needs to be in there. So the question got asked about the lab schedule. There is an updated syllabus on the course website with the lab schedule on it that actually discusses the AB. So if you go to the course website under Getting Started Syllabus, the lab syllabus has already been updated with the new schedule. Next week, and this week is going to be and was the analysis of a prescription tablet using thin layer chromatography, and then you can find the rest of the labs also underneath that syllabus as well. I'm just going to ask questions about the lab. Yes, you're always free to answer questions about lab. I'm not going to do it for you, but if you have like questions, like you're free to ask them, and I can always just tell you, like, I think that's something you need to work on your own. But if you have questions about the lab, you're free to ask them. You're welcome. So the question was asked, what are you looking for in the lab? What you're looking for in the lab is initially what you're looking for are the retention factors, the RFs, and this is what you'll be using when you do your data analysis. So with thin layer chromatography, on page 26 in the lab manual, it gives you the formula for retention factors. So we're not looking at how they move relative to each other. I mean, that's effectively what we're doing, but what we're looking for is how they moved relative to the solvent. So you start with a TLC plate with 5 spots. I'll just draw 4 so it's a little bit easier to see. And you're going to finish with a TLC plate. And sometimes they move a lot, sometimes they move a little, and sometimes you have multiple spots. So the retention factor is defined as the distance traveled divided by the distance traveled by the solvent. In this case, it's called the solvent front. So the distance traveled by the solvent is the distance between your start and finish lines. Now, yes, the solvent also traveled up this little bit as well. A little bit well there as well. We don't care. We care about what happened when it came across the analytes that we're looking at. So this is your solvent front. It's just called L. And then what we're looking for is the distance the materials themselves traveled from the starting line to the final, where it's finally stopped. And your RF here is going to be defined as the D over the L. Now, retention factors, again, are not unique. So not like one compound doesn't have its own unique retention factor for a given solvent mixture. So what we're looking for are consistencies. And for this hypothetical plate, these 2 spots and these 2 spots are consistent. So let's say this is reference 1, reference 2, reference 3, and this is your unknown. So if we have outside information to tell us that, well, the unknown can only contain reference 1, 2, or 3, we can say that the unknown contains reference 2 and reference 3 because these have the same retention factors. But if we don't know that about the material, let's say we just don't know what's in the unknown and we run some references, the only thing we can say at this point is that these are consistent with these retention factors. They are not necessarily proof. And this is the issue with TLC, is that unless you have that outside information, you can't prove definitively that that's what's in your material. Now, what we can say with the unknown is that it definitely does contain whatever reference 1 is. So we can definitely say if it doesn't contain something, but saying it does contain something, you need to know that your unknown only is limited to certain compounds. But anyway, the way we would prove that is we look at the retention factor between these two spots. We'll look at the retention factor of this spot and this spot and compare it to the retention factors of other materials. Now, the nice thing about TLC is that you can just kind of look at it underneath the UV light. That's why we like TLC. You can stick underneath a UV light and say, oh, when I stick underneath the UV light, I could definitely see they were side by side. The reason why we want to work with retention factors, though, is let's say if you've got like 20 possibilities. You can't run them all on the same plate. This is just not practical. And you're probably not going to draw all these plates the exact same way, so they're not going to be all the exact same wavefront. So what you can do is you can run different compounds on different TLC plates and then use that retention factor between plates. So that retention factor should be consistent between plates as long as your solvent ratio doesn't change. So if you're still working with that 1-to-1 hexane acetate, the RF for caffeine is going to be the same regardless of whether you run a 20-inch plate or 20 centimeter plate or 5 centimeter plate. So for the data analysis, you're trying to find the RFs by looking at how far the solvent traveled versus how far the spot traveled, and then comparing those RFs of your spots to the RFs of the spots for the unknown, and from there trying to see if you can determine like what was in your unknown. Now, the other point of this lab is to let you see the difference between a good solvent system and a bad solvent system. So definitely for one of these solvent mixtures, and I'm not going to spoil it because there's a group that's doing the lab next week, it is an absolutely awful solvent mixture because nothing happens. Your RFs are pretty much all the same for all materials. And then there's a solvent ratio where you do get really well-defined RFs for all the materials, so it makes it easy to determine what the unknown contains. So definitely when you're doing that data analysis, keep that in mind. If all your RFs are roughly the same, it's going to be really hard to resolve one compound versus the other unless you have a really long plate. But if you've got a good solvent mixture, everything kind of gives a nice, pretty well-defined RF, so it's not like an RF of 0.1 versus 0.15. It's like an RF of like 0.8 to 0.3. You can clearly see those even on small plates. That's the ideal solvent system. All right, so at the end of the live stream, thank you, Elijah, for stopping by. It's always good to talk to you. And again, if you ever have questions, please feel free to ask, even if you're not in the course. Last live stream for this week. Next live stream will be next Monday. Again, if you're in the B schedule, remember that you're showing up to lab next week. If you're in the A schedule, you're not showing up. Definitely plenty of online labs for you to do during your time off. All right, I'll see y'all next week.